Alright, so this is example 1. Again, I'm going to assume that you have read this problem and that you've tried to work this problem. So let's get started. Basically, I have an electron that is placed at some point in space where there is a uniform electric field. So let me draw an X and a Y axis. The electron is placed at 2 centimeters, 4 centimeters. So it's going to be 1, 2 centimeters to the right and 1, 2, 3, 4 centimeters up. So let's put the position right there. So I've just got some markings here to indicate apparently centimeter spacing. And then the electron is moved to a point at -3, 7. And so I've run out of space. It's going to be -3 and then up 7. So let me move this coordinate system down. Put it right there. So I'm going to go over 3 and then up 1, 2, 3, 4, 5, 6, 7. Somewhere up here. It doesn't really matter if it's drawn accurately. I'm going to calculate the work that's done in terms of just the symbols. Alright, so I have numbers for all of these things, but again, let me just write this. Let me use some symbols to make all of the algebra cleaner. So let me call the first position that it's at x1, y1, and then let me call the position that it's moved to x2, y2. Alright, so I've got an electron, which means I immediately know that the charge of the particle that I'm moving is negative the elementary charge. So I'm going to take it from here and move it to here. Now, the uniform electric field is basically going to exert a force on that charge, and that's going to require me to do some work to move it. I'm either going to have to do positive work if I have to push it against the force that the electric field exerts, and I'm going to have to do negative work if I have to pull it against the field's force. So the uniform field is going to look like this. Points in the x direction. And all of the, so if I'm drawing these field lines, all of the field lines should point in the same direction, and they should be roughly equally spaced, because that's what a uniform field looks like. Alright, so I know what the potential difference between any 2 points in a uniform electric field is. And that's useful because if I know what the potential difference is, then I can calculate what the change in potential energy is. And the work that I have to do to move the charge through the electric field is just equal to its potential energy change. Right, so I can see this if I draw the analogy with gravity. If I take a ball that sits on the floor, it has 0 gravitational potential energy. I then am going to raise the ball some distance. Let's say that I raise it a distance h. How much work was required to do that? Well, the change in the potential energy of the ball is its mass times the gravity acceleration constant times that distance h. And I know that, so I've increased the potential energy of the ball, and I had to do work on it for that to happen. So the work that I do is just equal to the change in the ball's potential energy. If I start at the top and I lower it, then the ball is going to lose potential energy, and it takes negative work for me to do that, because if I just let the ball go, it would actually fall to the ground. And to keep it from falling all the way to the ground, I have to pull up on it. So I'm doing negative work as I let it fall to as I lower the ball at a constant speed. I would have to do negative work to do that. So the same thing's true here. The work that we're looking for is just going to be equal to the change in the charge's potential energy, and that change in the charge's potential energy is going to be due to a change in electric potential. So I need to calculate what this change in electric potential is first. In a uniform field, the change in the electric potential is the uniform field strength times the distance that you travel. And the tricky part here is, or the thing that you got to make sure that you are aware of, is that this distance traveled is the distance in the direction of the field. And there's actually a negative sign here. So it's negative electric field strength times the distance that you travel in the direction of the field. Now, distance is a positive number, right? If I'm talking about how far away something is, it's always a positive number. So let's talk about, instead of calling this the distance that you travel, let's say it's the displacement in the direction of the field. And displacement can be positive or negative. So if I start here and I displace 1 meter in the x direction, then my position moves to the right. If I displace -1 meter in the x direction, then my position moves to the left. So if I talk about d as being the displacement, then it could be positive or negative. And if I travel in the direction of the field, then it's going to be a positive number. And if I travel in the opposite direction of the field, it's going to be a negative number. Now that's important. You got to know what the displacement in the direction of the field is. So if I go back to the problem that I have, I see that my electric field is just in the x direction. If I displace to the right, the potential energy, or excuse me, the electric potential is going to go down. If I displace to the left, the electric potential is going to go up. To calculate the potential difference between my endpoints here, so I've got x1, y1, x2, y2, I need the displacement in the direction of the field. So what I actually need is this distance that it travels in the x direction, because that is the direction of the field. So we call this distance, well, let's call that a displacement. Now clearly that displacement for this case is going to be a negative number. But in general, because the electric field points in the x direction, that displacement is going to be, so that's going to be x2 minus x1. Where did I end up? Where did I start? The difference in those is the displacement. So that distance d is x2 minus x1, which means that the change in electric potential along that path is going to be the electric field strength with a negative sign, x2 minus x1. So note that in our example, this x2 minus x1 is going to be negative, so the change in potential is going to be positive. Alright, so the change in potential energy of the electron is going to be Q times the change in potential, and we know what the charge is. That's negative E, and then I've got negative capital E for the field strength. So it's going to be E x2 minus x1. That's the change in the potential energy of the electron, and that then is the work that I have to do. So for this problem, E is the elementary charge. The negative sign that I put in front of it for to indicate that it was an electron is gone now, right? So this and this cancel. So this isn't the charge of the electron, this is the elementary charge. So that's going to be 1.60, I think it's 1.602 times 10 to the negative 19, and that's coulombs. And then I've got this electric field which points in just the x direction, and I'm told that it has a magnitude of 10 newtons per coulomb. And then x2 and x1 are given to me, and these are given to me in centimeters, so I do need to be careful here, because this newton has, well, if I write that out in terms of the SI base units, it is a kilogram meter per second squared. Right, so there's meters in there. So if I multiply this, if I multiply this electric field by a displacement in centimeters, the meters and the centimeters are not going to combine. Right, so they're not going to be able to combine to give me joules for my energy. So I got to make sure that I pay attention to that. The easiest thing to do if you don't want to do unit conversions afterwards is to just say, well, I'm going to write down what these positions are in meters. I'm given the positions in centimeters. Let me just write them down in meters. So the first one is 2 centimeters. The second one is -3 centimeters. That's going to give me 0.02 and -0.03 in terms of meters. So the first one is 0.02 meters, and the second one is -0.03 meters. There we go. So I have all the values that I need to calculate this work that needs to be done.